will be about gamma rays. And why inverse Compton and synchrotron were so relevant is that high energy gamma rays are dominated by non-thermal radiation, mostly from energy losses. So what I introduced before was the fact that you can have as a continuous loss inverse Compton, where you have photons interacting with electrons. So electrons are typically produced as from cosmic ray accelerators, and then they do interact with photons at lower energy, and the photons can be upscattered at higher energies. So as a matter of fact, is like an elastic scattering, where you get the electron or positrons, which are still of the GeV in the GeV range, and the photons that are upscattered at few GeV, depending on the energy of these low energy ambient photons. So you can work out from this full Klein-Nishina regime, so the relativistic regime, what is the energy of the outgoing photons. But just to have a proxy for you to remember, the final photon energy is related to the initial photon energy by the Lorentz factor to the square of the electron or positrons. So if you have a cosmic ray electrons accelerated up to GeV energies, and your radiation field is of the order of the electron volts, then you get out photons at the MeV energies. So, but what is it really, this interstellar radiation field? Well, is the ensemble of photons that is produced by star within our own galaxy. So you have a typical peak of the interstellar radiation field at a few micrometers from the emission of the optical light from stars. And then you have a second peak of the interstellar radiation field at 100 micrometers that are the photons that are absorbed, optical photons are absorbed by the dust and then re-emitted in infrared. And then finally you have this guaranteed emission of photons, of low energy ambient photons from the cosmic microwave background. The interstellar radiation field, the distribution of photons and energies depends on the position in the galaxy. So the largest is, for example, the amount of stars that you have. The largest is the stellar light component, or the infrared one if you have substantial dust. So the farther you go outer in the galactic disk, the least contribution you have from the optical and infrared components, while the CMB is the guaranteed contribution that you have basically everywhere in the galaxy. The C is constant. Yeah. You can describe effectively this interstellar radiation field with black body radiation, and you can work out what are the energies, the mean averages of this black body spectrum. So you see that the starlight peaks at about 0.3 electron volts, the infrared at 10 to the minus 2, and the CMB at around 10 to the minus 4 electron volts. So if you were to plug in again those numbers for the photons field in this equation, you see that you expect photons from MeV to GeV. What can accelerate electrons that can then lead to these continuous energy losses like synchrotron and inverse Compton? You need leptonic accelerators. We have evidence for accelerators of leptons, which are pulsars and pulsar with nebulae. They do emit, are detected from GeV to TeV, and they do emit either from the prompt magnetosphere, where you have the photons directly created along the magnetic field lines, or through this secondary emission of inverse Compton. So you have the inverse Compton of electrons produced by the pulsars that then upscatter low energy ambient photons around the pulsars up to TeV energies. And interesting enough, LASO has detected 12 pevatrons, so up to very high energy, and 9 of them are actually detected close to pulsars. So there might be good chances, although it's not settled yet, that pulsars may be pevatrons accelerators. So we then can go, really, now that we have the idea on how cosmic rays are produced and accelerated in astrophysical sources, and then how they lose energy by leading to secondary gamma ray emission, we can go into more details about the gamma ray sky at different energies. So this is a typical plot that you may have seen in your life, where you have the sensitivity, the flux sensitivity, so an energy divided by an area and a second, as a function of energy. And typically the sensitivity gives you an idea of how to compare different experiments, because you use a standard candle, a very bright source, which is the Crab Nebula, and you compare different experiments by requiring that each of these experiments can see the crab at more than 5 sigma. So, as mentioned before, you can detect cosmic photons mainly with two techniques, either in space or on the ground. In space, you are limited by the fact that you need the photons to be contained within the calorimeter on the detector in space, and so there is a limit and a maximum energy that you can achieve. I will discuss this sub-GeV energy range later on. But here we have one detector which is really making breakthrough science since 2008, which is the Large Area Telescope above the Fermi satellite, which is a pair-conversion telescope which measures high-energy photons from, say, 100 of MeV up to 500 GeV, more or less. Then if you go higher in energy, you have to rely on ground-based detector, either imaging Earth-Cherenkov telescopes or Watt-Cherenkov tanks. So the story of cosmic gamma rays detected in space dates back the end of the 70s, where you had the first telescopes on satellites launched, and the first sky map ever taken of gamma rays here in 72 with the OSO satellite. There were only 300 events. Now we have, I don't know, how many million events. And it was really in the end of the 90s with the IGRET satellite that we started to do gamma ray astronomy by measuring excess of photons in the direction of known cosmic ray accelerators and sources. So we had 200 sources identified in gamma rays in the soft GeV regime. And lately, with the LAT, we really can see the full high-energy sky from about 20 MeV, as I said, up to 1 TeV, with an extremely good angular resolution. And above all, we do see the full sky altogether. This is an advantage that satellite instruments do have with respect to ground-based instruments, which can only be pointed to the specific source. This is the full sky in galactic coordinates. So these longitude coordinates here running along the galactic plane, and the galactic latitude here above and below the plane, where you see a very bright emission. This is from our own galaxy. I'll describe a bit where it does come from. But what I want you to focus on here is on the left part of this image, and on the right part one is a comparison between the IGRET satellite image and the 9 years of observation of the LAT. Those are only the counts, so they are only directly the photon events that are classified as such by the telescope. So it's not the flux, it's really just counting the number of photons that hit the detectors. And you have an amazing image of the sky, where you can see that the image has sharpened a lot with respect to 20 years back. And you have many more bright hot spots here at higher latitude. So the game is then what where these emissions come from and what we can learn about astrophysics. So the gamma ray production mechanisms, again, boils down to cosmic rays. So you need cosmic ray accelerators or exotic physics, inject cosmic ray particles or prompt photons that then leads to the production of synchrotron. There are also other secondary emission like Bremsstrahlung, inverse Compton, and pion decay. So let's have a look a bit better and more details about this Fermi lat sky, but in general, the sky at GV energies. So you have this very bright emission from the galactic plane, which traces really the gas in our own galaxy. And why is that? So as I explained, in the plane of the disk, you have plenty of galactic sources like supernova remnant and pulsar wind nebulae. They inject protons and electrons, typically at GV energies. And those protons and electrons, they do travel deviated by this diffusive transport within the galaxy by feeling the magnetic field. And before they reach Earth, for example, before they reach the AMS instrument, they can interact with the interstellar medium. If they do so through these either catastrophic losses or continuous losses, they produce photons. So you have three main mechanisms to produce photons in this energy band. So one is through the decay of pions that are produced in proton-proton interaction. So you have a cosmic ray protons interact with an interstellar medium proton. It produces mostly pi zeros. The pi zeros then decay into two photons. This is, of course, you get a distribution of photons that reflects the distribution of pi zeros, which are boosted by the scattering between the proton and the protons. And here, in this column here, you have the expected gamma ray emission that you would have out from this process. And you see that the pion decay gamma ray emission really closely follow the gas, so the target material of the interstellar medium. You can also have bremsstrahlung when an electron, so a cosmic ray electron, feels the potential of a proton, an interstellar medium proton, and emit gamma rays. So the energy at which the gamma rays are emitted depends, of course, on the energy, again, of the cosmic ray electrons. But if you have GV to TV electrons, you have GV to TV photons. And again, the spatial distribution of photons that comes out for this process follows the target material. This is a general statement, which also holds true for inverse Compton. So again, when you have a low energy ambient photon, which is upscattered at gamma ray energy by a GV electron, then what the distribution of photons that you would expect is much smoother than the other two cases, because here the target material are the low energy ambient photons. So you expect some disk shape where you have the starlight and infrared components, but then you have a very smooth transition of the gamma rays because of the large scale extension of the CMB. So I said that you also have bright spots that you can just see by eye. So, but what are they? So those are gamma ray sources that are identified as excesses, like point-like excesses above the background here, for example, from the galactic diffuse emission. And then what you do, as a matter of fact, is you collect all those bright excesses that you have in gamma rays. You call them gamma ray point sources. And then you go back to your multi-wavelength knowledge of astrophysical emitters like AGN or star-forming galaxies or catalog of supernova remnants or pulsar wind nebulae that you have accumulated through other observations. You do a cross-match, basically like just a positional cross-match mostly. And you can identify objects that are present in other catalog, and you can claim that there is an association between your gamma ray source and your multi-wavelength counterpart. So you can claim that this point here, for example, is an AGN. If you were to lack this kind of association, you are left with a point source, which is an excess in gamma rays, but is not associated with any multi-wavelength counterpart. So what is that? Well, you have now about 5,000 sources that are identified as bright hotspot in gamma rays. 3,000 of them are associated with AGN, hundreds of them are pulsars, but there are about 2,000 that are left and are considered as unassociated sources. So the unassociated sources are mostly located along the galactic disk, and there is because in the galactic disk it's much more difficult to identify a point like gamma ray emitter because you have this very bright emission from the galactic disk itself. So how you can identify point sources in this kind of mess here? This is why the sensitivity of the LAT really decrease a lot going towards the galactic plane, and you have a peak in the number of unassociated sources towards the galactic plane. So what those unassociated sources can be? Well, they can be other astrophysical objects, of course, that do lack identification, but might also be some first signal of dark matter, and I'll discuss that later on. I want to mention about a specific class of gamma ray emitters which were making really truly a revolution in our knowledge of this kind of emitters, and those are pulsars. So pulsars were discovered at first in gamma rays with the processor of Egret, I don't remember the name. They were the Crab and Vela. But then it was through radio observations that the number of pulsars get really increased by a lot. And typically you can claim identification of pulsars through radio because you really see the pulsed emission which comes from the light beam effect. However, with Fermi, we started to see a lot of pulsars, and a lot of them were even not emitting in radio. So Fermi has allowed to get an increase, and really a huge increase in the number of detected pulsars, and above all on the number of millisecond pulsars, which are typically found in binary systems, are very difficult to identify in binary in radio because of eclipses that might be ongoing with the binary system, while in gamma rays you really increase a lot the number of millisecond pulsars, and now we have hundreds of MSPs just detected with Fermi. One interesting source of photons that is also intriguing a lot the astro community is the emission that comes from what we call higher latitudes. So if you cut away the galactic plane, you still have a residual emission here in blue of photons, which is not really coming from point sources, but is mostly like a uniform isotropic distribution of photons coming almost uniformly from all directions. And you can measure the spectrum, so the energy flux as a function of energy. This is called the spectral energy distribution. I will use that a lot in the following. You can measure the slope, the shape of the spectral energy, and this is almost a featureless power law with an index of about minus 2.3, up to a cutoff that you have at 200 GeV, which is due to extragalactic background light absorption. So why is so interesting to understand where these emissions come from? Because it is for sure the superposition of multiple components. So you can think about our own galaxy to be embedded within the universe, so it receives light from all galaxies around us, and also active galactic nuclei and other kind of emitters far away. So there is some guaranteed astrophysical contribution that goes in this isotropic diffuse emission, and there are several models which are calibrated on gamma ray analysis of individual point sources that can tell you more or less what is the percentage of this isotropic flux of different categories. But what is really interesting is that within this flux, there should also be some room, or at least you can look for some room for more exotic emission processes like dark matter annihilation in external galaxies. So there were two main transformative discoveries that the lab made and that are relevant also for new physics studies. One is the discovery of the Fermi Bubbles, which are extended structures that emerge in the high energy sky at around 100 GeV in the data of the LAT, with very, very basic cleaning of the data. You see those bilobular structure just appearing. Extends up to about 40 to 60 degrees in latitude above and below the galactic plane, and points towards the center of the galaxy. So it has also some multi-wavelength counterparts in radio and microwaves, although the multi-wavelength connection is not fully assessed yet, because we don't really know what is the engine that is sourcing this kind of emission. So there are several models. It might be, for example, that the origin of those bubbles, so let's call the Fermi bubbles, comes from the activity of the central massive black holes at the heart of the galaxy, or it rather comes from a bursty star formation history that it might be also supported by other multi-wavelength information. So although we don't really know what the origin is of those bubbles, what it matters for new physics searches in gamma rays is that we can characterize well its spectral shape and its spatial distribution in the sky. So if you have a component that you can really, for which you can describe the spectrum and the spatial distribution of photons, then from a pheno point of view, this is all what you need to make some basics inference about new physics, and I'll show that mostly tomorrow. The other big discovery was the long sought after fact, probe that supernova remnant can accelerate protons. And this was through the measurement of what we call the Pion Bump. So as I mentioned, the most frequent way in which you can produce photons from proton-proton interactions is through the decay of neutral pions. And you can work out how the spectrum should look like, but if you have an energy distribution of pions, and each of those emits two photons in the back-to-back in the rest frame of the pion, then you expect a spectrum for the gamma ray radiation, which is peaked at around a few GeV. And this is the so-called Pion Bump. And there was evidence detected in multiple supernova remnants with gamma rays from the LAT that indeed supernova remnants do accelerate protons. But what happens for higher energies? Well, for higher energies, we have a kind of transition in our, let's say, perception of the sky from a sky which is mostly dominated by the diffuse emission at a few GeV, as I showed for the LAT, to a sky which is mostly dominated by point source-like emissions, as it is the case for example, the LASO sky. Of course, the sky is like that only because our instrumental sensitivity. So it's not like that because there is a transition in the mechanisms for production. There is perhaps a transition in the effectiveness and the cross-sections for these mechanisms, but as a matter of fact, this transition is strongly dominated now by the fact that we have instruments with much less sensitivity to the diffuse emission at the TeV scale rather than the GeV one. So let's have a look at the point sources at the TeV. So you can still do some survey game at TeV, although you need to just cumulate pointings one close to each other to make an effective survey with instruments that can only point with a reduced field of view to a given region. So this is the galactic plane survey from Hess, where you see really, you don't see any longer this very bright diffuse emission as it was the case for the LAT, but you see rather many small-scale structures, which are mostly supernova remnants and pulsar wind nebulae. If you consider the contribution of different source classes to these catalogs for the Hess, you have that about 40 of them out of 80 are non-identified, so still they do lack association. Most of them are supernova remnants and pulsar wind nebulae. And finally, with with the LASO at sub-PV energies, we had the first detection of actually cosmic ray accelerators up to the PV scale. I mentioned them before. We have the evidence for 12 accelerators, mostly associated with pulsars, and this was really a breakthrough measurement for the high energy gamma rays. I also would like to mention the emission from the galaxy that would come at those sub-PV energies, which has been measured by two arrays, so LASO here in China and T beta IS gamma in magenta. So this is the emission that our own galaxy, as in the case of the LAT, the bright emission on the disk, would contribute to at sub-PV energies. And why is this interesting? You will realize that more tomorrow. Yeah.
So why the Fermi bubbles don't show up there?
Yeah, so the Fermi bubbles are, so this is a model map. Because you cannot really see the full sky at those energies, you have arrays. So this is, for example, the field of view of LASO. You see here, so LASO can only make an effective survey in this very small region. And this is T beta is gamma, more or less, the field of view. So the effective field of view, combining the observations. And here is the model map. So what you do expect at this very high energy. This brings me just to make a comment about the spectrum of the bubbles. So there are current upper limits that are set by Hawke at 100 TeV on the Fermi bubble spectrum, and we don't see any cutoff in the bubbles, but we don't have any detection either. So the upper limits from Hawke are compatible with a spectrum that is keeping going up to TeV energies for the bubbles. But here we are talking about sub-PV, so it becomes even more speculative since we don't know the model that is sourcing these bubbles to make predictions for what you expect at PV. And in the future, we have the Cherenkov telescope array that will come online, so with one northern site in La Palmas, very nearby, and one southern site in Chile. Why it's supposed to bring quite some interesting result, a breakthrough result, is because on the one hand, the much higher angular resolution with respect to current water Cherenkov detectors. So you can reach, let's say, a few 0.5 degrees angular resolution at 100 of TeV, which means you are very sensitive to see point sources at those energies. And of course, the flux sensitivity. You need to go down in flux to be able to see a lot of them. And so this is the energy flux sensitivity, the function of energy for CTA North and CTA South. These lines will be definite only when the array is built and you have the final setup. But again, it is expected to give an improvement at least of order 10 on Hess and the current imaging Cherenkov telescope. And what we expect from CTA is to be able to really survey this galactic plane with very high angular resolution. So if we were to build the models for the sources that we know, so this is typically what is called the log n log s, so the number of sources as a function of flux. It gives you an idea on how many sources per unit flux you would have for different populations. This is the currently known sources. You see the flattening here is a flattening that originates from the fact that current instruments have a sensitivity limit at 10 to the minus 12 centimeters square per second. While with CTA, we expect to go down in sensitivity and to be able to see many more sources. Many more sources would mean to understand how the sources are distributed, what is the origin of the unidentified ones, and be able to look for new physics on top of what we know already. So now just switch to this presentation because it comes the part which is more of interest for me in general, but also perhaps on all of you, since this better matches the talk. But I really think everyone needs a broad introduction about cosmic rays and gamma rays in order to be able to do looking for new physics with astroparticle observables. So then let's start. As I said, everything I said up before was mostly about discovering new astrophysics. Now is about trying to probe fundamental physics with astroparticle observation, and I think I'll go back to fundamental astrophysics at the very end of my lectures tomorrow. So why do we want to look for new physics with astroparticle? But first, because we have strong motivations that we need physics beyond the standard models. Secondly, because it happened already that we found new physics with astroparticle or astrophysical observables, like the case of neutrino oscillations. And interesting enough, astroparticle and the high energy astrophysics domain is plenty of anomalies that sometimes we really have an hard time to explain with standard astrophysics, and why not thinking about how to invoke new processes or new effects in order to explain those. So if new physics is there, you always expect some sort of astrophysical signatures, and those are the ones that you can leverage upon, if not for making discovery, to constrain new physics scenarios. So astroparticle observable can be either a discovery tool, where you want to interpret anomalies, and if you are lucky to find one that is really due to BSM, but also to constrain the parameter space for your theories. Of course, there are quite some challenges because we are in a domain where you have you are dealing with density, temperatures, and sizes which are not comparable to your lab experiment. So it means that you do not really control your environment, and the systematics are large. So you need to somewhat study your standard astrophysical environment if you want to make any kind of claim that you want to say robust on new physics observations. So in what follow, what I would like to present to you, since the domain is quite broad, are few lines of research that have basically been driven by my curiosity in the last few years that can help you just schematize how indirect detection of new physics works. And here I'm referring more generally to new physics because most part of the indirect detection is about dark matter, and there will be a big chunk of my lectures. But you also can do searches for more general BSM, like axion-like particles produced in stars that do not have any link with dark matter. But let's start with dark matter. So you have seen in Tracy's lectures that we have overwhelming evidence for dark matter at multiple scales, from the scale of galaxies, few kiloparsec, up to the cosmic microwave background. And what those astro observations are telling us are some basic properties that dark matter should have in order to be responsible for all of them at once. And we can also measure with quite good precision what is the average mean density of dark matter cosmological scales. However, it doesn't tell us much about what dark matter is in terms of more fundamental theories or parameter space. So we have a vast parameter space in mass and interaction strength. Tracy talked about most of the candidates, but here I just recap that you have a regime where dark matter particles mostly behave like waves, and from a pheno point of view, you can leverage on these wave-like phenomena. You have a regime where particle dark matter behaves more like particle, and then you have a dark matter also at very high masses, where you can have, for example, primordial black holes to be good dark matter candidates eventually. So no matter what your particle or non-particle dark matter candidate is, and your theory is indicating you, whenever you want to engage in some identification strategy, you need to have some sort of signatures that you need to look for. So you always have some prejudice in what kind of search you are performing because it comes from your theory motivation. But you also have some imposed driving line from what the data are telling you and what data are available to look into. So let's have a look at the broader indirect probes for dark matter. So indirect probes for dark matter are based on what dark matter can do in a given environment. So the more standard indirect detection that most of you may have heard of is based on the fact that dark matter can self-annihilate or decay either today in galaxies or in the past, injecting energy and particles in the environments. And those energy and particles will have an effect on the body or on the environment where they are injected into. You can also exploit if your, for example, candidate only interacts gravitationally, gravitational interactions. You had lectures about large-scale structures and also the lensing. So typically, you can have dark matter structures to be felt by more baryonic structures and to lead to phenomena like gravitational lensing that can also inform you about some properties of dark matter. And finally, you can have dark matter particles or non-particle dark matter being captured or scattered or accreted onto objects of different natures, from planets up to very compact stars, like neutron stars and black holes, leading to some signatures that you can look for. So one can recap the signatures from different dark matter candidates onto a more astroparticle observable space in this schematic way, which it's not meant to be fully to cover all possibilities, but just give you a few ones. So you can exploit this accretion onto compact objects by looking, for example, at gravitational waves or superradiance, and it won't be the focus of my talk. You had lectures about lensing and structure formation, where you really exploit the gravitational interactions of dark matter with big baryonic structures. And what I'll focus on is rather how you can exploit the high energy sky from radio up to gamma rays in order to detect these or whatever, constrain those kind of candidates. So I'll focus on what we call traveling cosmic messengers. And the CMB probes were already discussed by Tracy. So let's start from some basics about what are the astrophysical ingredients that you need in order to try to look for dark matter. So first of all, first thing is that the dark matter flux of your particle, so whatever is the number of particles per unit area and second that you expect, is directly proportional to the density of dark matter particles in the target of interest. And the dark matter density is related, a number density is related to what we call the dark matter energy density, which is nothing else than the number density times the mass, which is some quantity that the most astroparticle phenomenologists like to deal with. Two important facts. The dark matter particles in the halo of our own Milky Way are almost at rest because they are very slowly co-rotating with the galaxy. And also the dispersion, you can work out the dispersion velocity of the velocity distribution that dark matter particles have in the galaxy, which is well approximated by Boltzmann. What is important to take away is that dark matter today is not relativistic, and in the halo of our Milky Way, it's almost at rest. So any process is, as a matter of fact, occurring at basically velocity equal to 0. And this simplify the things quite a lot. So, but how is dark matter distributed in the halo of galaxies? Well, the dark matter distribution, density distribution, energy distribution as a function of galactic radius is really one of the most important systematic theoretical error that you can have, because we don't really know, for example, in our own Milky Way, what is the dark matter profile down to the center. We can use galactic rotation curve of the Milky Way to infer the dark matter distribution down to a few kiloparsec. And you see that no matter what the parameterization of your dark matter distribution is, they all agree at larger radii because you have strong constraints from the measurement of the dark matter local density and also the galactic rotation curve. However, below these few kiloparsec, you have to rely on simulation of structure formations, of simulation of galaxies, where you can identify what would be the behavior, more or less universal, of dark matter halos in different type of galaxies, but you cannot really discriminate or infer what is really the dark matter distribution in our own. And if you want to use galaxy simulations to infer the dark matter behavior in the inner part of Milky Way-like galaxies, you end up having different answers depending on the type of baryonic feedback that is used in different simulations to try to simulate the structure formation. So you had a few lectures about structure formation and simulation, so I won't go into the details, but if you want to infer the Milky Way distribution by analogs in simulations, you need to be driven by two main criteria. You have to select only Milky Way-like halos, so with a mass which is consistent with the dynamical mass measurements of our own Milky Way, and then you have to find a way to extrapolate at a small scale, and this is the big challenge. So, long story short, we have large systematic uncertainties when we want to look for example, dark matter towards the center of galaxies. And on top of this, what most of the simulation of galaxies do predict is that for every big halos out there which contains and form galaxies in the heart, then you also predict, the simulations of galaxies also predict the formation of bounded structures that are hosted by the gravitational potential of the host, which are called the substructures or clumps or subhalos. And why are they relevant is because the mass distribution and the number density of those small halos can discriminate between different type of candidates, like hot and warm dark matter, as you've seen in other lectures. But from a Fino point of view, why they are so interesting is that you can leverage upon the specific spatial signatures that they would induce. Let's suppose you have every of these halos emitting photons. You would expect a very bright sky with small hot spots that comes from those substructures, as just you can really match the photons flux to this density map, because photons are not deviated in galactic environments. While if you were to have less halos, you would expect less point sources, and if you were to have only the smooth distribution, you wouldn't have any special distribution of small scales at all. So you can really leverage on these angular signatures in different ways, looking for anisotropies, looking from unassociated subhalos, so point sources that are not associated, that could be sourced by dark matter, or cross-correlation with multi-wavelength catalogs. But let's have a bit better look about the emission of high-energy photons from particle dark matter candidates. So as I said, you can have this emission through self-annihilation of two dark matter particles into standard model photons, or the decay of one mother particle. And because of the fact that the process occurs at rest, as I mentioned, because of the low velocity of dark matter particle in the halo, the center of mass energy is directly related to the mass of the dark matter particle, which means that if you were to investigate a particle of a GeV mass scale, then you expect photons in the GeV range. So you have a direct link between the center of mass energy, of the mass of the dark matter particle, and the energy scale where your photons would arise. So if dark matter is below the MEV, it cannot produce nothing more than photons. And the signal would be a line, so just a monochromatic line, because of the fact that the process occurs at rest, at half of the dark matter mass, or at the dark matter mass energy in case of decay. And the spectrum is nothing else than the line, broadened either only by the energy resolution of the instrument, and there is a bit of broadening by the velocity distribution that the dark matter has in the halo, but is typically subdominant with respect to energy dispersion. So as soon as you open up the channel for electron-positron production, that you can see that in any model that you have for your particle dark matter, you start to produce other particles, so muons, taus, pions, and so on and so forth. So you have a broader energy distribution. This is the spectrum as a function of energy, which takes contribution from these gamma ray lines, the final state radiation. So there are the photons that are emitted when you have two-body annihilation into leptons, and then you have this secondary production that comes from the fact that you produce, you have an hadronic decay of those dark matter particles, and you can have pi zero that are produced that leads to photons. So that's why you have a broader energy distribution, even if your center of mass energy was always at the level of the mass. So before concluding, I want to give an overview about how do we look for lines for like dark matter. So where we only have photons that are produced back to back. There is a very simple way to relate the mass and the energy. So if you have a dark matter particle mass at the microelectron volt, you have radio lines emitted. If you go up in mass, you can go up to X-rays or even GeV domain if you have GeV masses. So what is in are the main quantities that relates the fundamental physics part to the flux of observed photons are, so the rate, this is the rate per unit energy and volume, which contains the decay rate, in this case, because we are talking only about decay into photons, the dark matter number density, and the spectral energy distribution. So you can then get the rate per steradiant in the case of isotropic emission, as we think is the case for dark matter. And then by integrating this quantity over the solid angle and along the line of sight, we can get the gamma ray differential flux. That is the quantity that we need to compare with data. So in this business here, the rate, the fundamental rate, depends on the dark matter density, which is a function of radius. So as a matter of fact, we have always to integrate along the line of sight the dark matter density, and we can define this geometrical factor here is sometimes dubbed D factor in case of decay and J factor in case of annihilation. And it just boils down to integrating along the line of sight in a given direction your dark matter density, and then integrating over the angular variables. If you do so for a typical dark matter distribution which is peaked towards the galactic center, this is the map that you expect in latitude and longitude for dark matter decay. Where here is the galactic center, you expect a bright spot because of the parametrization that has been used. This is a typical Navarro-Franco-White parametrization of the profile. You would expect something smoother if you were to use, for example, a chord distribution of dark matter. So the prototypical example of looking for lines in this business is from sterile neutrinos dark matter. So in this case, the sterile neutrino will mix with active neutrinos by inducing the radiative decay of photons mediated by this loop here. And the decay rate of sterile neutrinos can be directly written in terms of the mixing angle and the mass of the sterile neutrino. So the parameter space of interest for this specific dark matter model is the mixing angle, or the sine square of the mixing angle, as a function of the sterile neutrino mass. And you would expect a line at half of the neutrino mass. So in this case, what do we do to look for lines for sterile neutrino dark matter? Well, we have prediction for sterile neutrino to be at the keV range, so we have to go in the X-ray band. And this is something that is been played regularly in the past, where you measure the rate, so the count rate of the X-rays detected by some telescope as a function of energy. You collect these points in black here, then you fit with your model, but your model is an astro model, so has to be informed about what is the astrophysics going on at those energies, and then you identify perhaps some excesses in your model. So this was what occurred back starting from 2014 with data from XMM and Chandra, where there was some excess power at 3.5 keV. detected from different targets and from different groups. So whenever you have an excess, then you can try to fit it with a Gaussian line, and people were found that actually a Gaussian line was resolving this issue of excess here, giving a better fit. And so you can then reinterpret this anomaly in your parameter space for sterile neutrino, because if this is a non-understood line, it could also be sourced by decay of sterile neutrinos. So you can put these detections here as closed contours, so from different observations in this parameter space, and those were claimed from, as I said, different instruments and different targets, so quite convincing. However, there are two things that you can do to investigate this kind of possibility further. So one is you look for more ununderstood astrophysical processes. So is there any atomic line that can mimic a new line at 3.5 keV? The answer for the moment seems to be no, and so even stronger for dark matter. However, you have another thing you can leverage upon, which is you can look for dark matter in other places where do you expect a similar signal. If you were to find one, great, Nobel Prize. If not, you can set constraints on the parameter space. And those constraints on the parameter space can be as strong as to making you able to exclude the interpretation of the 3.5 line in terms of sterile neutrinos. And this is what happened. The leading limits are now from the Berkeley group, are not shown here, are rather a bit lower here, and are very conservative limits in the sense that it's very hard, including systematic, to push them up. And are actually derived by accumulating a lot of blank sky observation of XMM. What does it mean, blank sky? It means that you just take the full pointing that XMM never had, and you take all the pointings at high latitude in the galactic halo where there is nothing astrophysically interesting there, and you stack them together, those observations, and if dark matter is there compatible with the 3.5 keV line, you should get also a signal from the halo, because dark matter is distributed. We know that follows one parameters rather than the other, but you should expect some minimal signal also from there. And in this case, you can exclude all of those contours pretty convincingly, although the debate is not fully over, and I invite you to read through this really nice review of Kev Basajan. So the current constraint parameter space is constrained more or less like here. You have current X-ray constraint, which are a bit lower from XMM, the 3.5 keV line, which might be there, might not be there. And so what we really need are future progresses with eRosita and AstroH in order to further cut down into the parameter space for sterile neutrinos. Is over my time? Okay, no, then I stop here.
My question is a bit about this excess flux that you see in the galactic center in gamma rays. So, I guess there is a lot of controversy, I know, on that, but so I guess for it being dark matter, it for sure needs to be extended, thing. But you said, making the connection, I don't know if it makes sense, but in the beginning you said that a lot of gamma ray emission that you find in the galactic plane, you see it as extended, but it's not really extended, but there are source points in reality. So could that somehow play a role in that? Sorry.
It depends always on the scales of the extension. So if I go to the point source stuff that I don't have in this set of transparencies, but so along the galactic plane, you see extended sources like the supernova remnants in the Hess galactic plane, which are extended objects on the order of parsec scales. the emission from the galactic center excess, which in any case I don't think I will attempt to treat tomorrow, is much more extended. So it's extended on scales of kiloparsecs. Let me go here. Yeah. So this excess in gamma rays extends up to 10 degrees above and below the plane. So it's very hard to make it fit with extended sources. And above all, what is really driving the scientists crazy a bit is that this excess is pretty uniform in space, in the sense that whatever section or segment of the main region of interest you take, the spectral energy distribution always peak at around 2 GeV, and then is a smooth transition in space. So then what it can be, if I have time, I will go through that tomorrow. But if you want the excess to be explained by a smooth distribution of photons, then you need something smooth, so like dark matter. However, you can do further analysis with respect to the first one that were done starting from 2009 up to 2016, 17, to look for small-scale power that there is in this excess emission. And then you find some indication that you should have point sources below the detection threshold of the instrument. And so then you can go ahead speculating. But there is no? No, there is a way that make point source, but not extended one, really. Just point source below the detection threshold can make it up. Actually, is one of the most promising possibilities. With new data analysis, really. You have the same photon, you have the same photons, a bit more statistics, but it is really the way in which you analyze the data that changes, and that can give you information about the small-scale power that is in this photon. So it's a different way to analyze the data. If I have time, I'll go through it, and if not, please just ask me tomorrow.
Okay, more questions, comments?
So you mentioned that the density profiles are not very well determined near the galactic center. Do you see an important sensitivity to the prediction of the fluxes depending on whether you have a COSPI or a core profile?
Yes, actually. I can take back slides if I find it. But if we were to think about annihilation, you have yeah, it's here. So this is most relevant for annihilation because this integral along the line of sight for the dark matter decay is the integral of the density, just a simple power, because you don't have you have only one particle. So the difference between core and cusp is not so a big. It does not have a so big impact. But if you are talking about dark matter annihilation, that you have the dark matter density squared that you have to integrate. So any difference of order, let's say even 100 in the dark matter density in the very inner part, translate in order 1,000 or even more in the what we call J factor, so the integral of this quantity, which is directly proportional to the dark matter flux. So for annihilation, it makes actually a huge difference what kind of parameterization you use. This, let me just say that this is true for our own Milky Way. If you were to look at other targets like dwarf spheroidal galaxy, what you receive photons from the whole object. So as a matter of fact, you are integrating over the full structure, and the dark matter density profile does make a bit less of impact. But if you were to look for a dark matter signal towards the center of the galaxy, or if you were to set constraints on dark matter from photons from the center of the galaxy, then your constraint, your error bar or your band would just span 4 order of magnitude, even more, only because of the systematics that you have on the dark matter density. So that's why it's not very robust to use galactic center data, put aside the galactic center excess, to set constraints.
More questions, comments? I have one. What happened with these 3.5 KV line? I mean, if it's not dark matter, do we understand what
No.
it could be? No?
No,
clue?
no.
Nothing?
One of my questions for you is, I read a paper by a guy from Santa Cruz in the US.
Profumo.
Profumo, yeah. He was claiming it could be potassium, right?
So there were some
Yeah, clear.
there were some papers afterwards that it couldn't be potassium. Then I don't recall the argument, but I think I can send you the papers. I see me playing with the mic.
Okay.
Sorry.
I have one more question. I'm afraid I have just forgotten. What is this about? Oh yeah, remember, Irosita. Irosita has been there. They have had data for years now, right?
Yes.
They don't say anything about this
So Irosita is a bit complicated to use Irosita because it's a Russian-German.
I know, but the German side. Huh?
But the galactic center, I'm not sure what are the because you see, the galactic center is Perseus, and I haven't heard anything about Irosita analysis. I'm not doing anything.
All right.
Yeah. But it's true. I mean, Irosita should say something.
Okay.
Oh, so it might be the.
Okay, let's thank Francesca again. Let's. Very nice talk. Ah, yes. Sí.
Now, yes. Okay, I'm going to repeat some of the things that Francesca already said previously, but okay, then you will have more info in your brain, so you will be able to remember better, right? So, I mean, yesterday we left, we quit the lecture with this slide. Oops, again. So, as I told you, remember that there is a huge region in the universe that we cannot observe with protons or with photons, okay? And moreover, protons, remember that are charged particles, and then they get deflected by the presence of magnetic fields. So when we detect a proton, we don't know where is it coming from, okay? So here I show you the optical depth, something similar that what Francesca showed you before, has shown us before, right? In which you can see that above energies of 10 to the 14 eV, photons interact with the photon backgrounds in the universe, so we cannot observe the universe with photons at energies higher than this, okay? So we know that there should be super powerful accelerator cosmic engines. Why? Because we have measured the ultra high energy cosmic ray spectrum, okay? So please keep in mind that the energies that this super powerful cosmic accelerator reach are much higher than those reached at colliders, at man-made colliders, right? Like LHC, okay, for instance. So the sources of these neutrinos, of these ultra-high energy neutrinos and high energy neutrinos that high energy neutrinos have been already detected and ultra-high energy neutrinos should be detected also, right? Should be detected in the future. So I mean, we have GCK neutrinos, and look at this arrow. So from here, it's kind of guaranteed, these fluxes, and as I go down, they are more speculative. But for sure, GCK neutrinos should be there, because I mean, the protons will ultra-high energy protons that we are observing in the cosmic ray will interact with the CMB photons, okay, via the GCK mechanism that we saw the first day, and also Francesca has mentioned today, right? So I mean, these GCK neutrinos should be there, right? Is a guaranteed source. Then we have gamma rays, super accelerated cosmic engines, right? Or galactic nuclei. And then more speculative, we have topological defects or the decay of supermassive particles, okay? So we have a clear connection between cosmic rays, gamma rays, and neutrinos. And neutrinos and photons are a guaranteed byproducts of high energy cosmic rays, okay? So they have to be there. They have to be there, okay? So we have several types of neutrinos at high and ultra-high energies. We have first atmospheric neutrinos, which are produced by interactions of cosmic rays in the atmosphere. They have energies smaller than 100 TeV, right? So, and they are produced by these processes, okay? By the decay of charged pions and kaons, okay? Produced in the interactions of cosmic rays in the atmosphere. And these have been measured by many detectors. You know this, right? I mean, indeed, the neutrino oscillations were discovered by Super Kamiokande, thanks to the atmospheric neutrinos. Okay. We have also astrophysical neutrinos, which are produced by cosmic ray interactions at the source. Okay. When they are produced, they interact either with proton-proton or proton-gamma collisions. We will see this now. Okay, in more detail. And they have energies typically above 100 TeV, okay? And then we have the cosmogenic neutrinos, which are those produced basically by the GCK mechanism, okay? By interactions of protons with the CMB photons via the delta resonance. The delta is a subatomic particle, a family of particles, right, made of 3 quarks, okay? And then these have energies about 100 PeV. PeV is 10 to the 15 eV, okay? A PeV, okay? So they have really large energies. And they are produced in these sort of processes, okay? P plus gamma CMB, delta to neutron plus positive pion, or proton plus neutral pion, okay? And then we have also more exotic sources, I mean, like heavy dark matter, decays, and such things like this, right? So, I mean, look at this, because this will be the last exercise. So, I mean, this will be important that you keep in mind, okay? But, okay. So, we have hadronic, photohadronic, or neutron decay processes, okay? Hadronic, proton-proton interactions. What happens here is that are produced pions and also muons, and also, charged pions, neutral pions, and also muons, right? And these are the ratios of the energies related to the pion energy, okay? In this process, the neutrinos get roughly a fourth of the pion energy. In this one, a fourth also the pion energy, and the gammas, in this case, get half of the pion energy, okay? And these are the fluxes. But the most important thing I want you to keep in mind, right, is that the energy of the pion is the proton energy divided by 5. So this means that the energy of the neutrino is the energy of the proton divided by 20, okay? So when we have a cosmic ray interaction, the neutrino will inherit the energy of the parent proton divided by 20, okay? We have also photohadronic, in which protons interact with gammas instead of interacting with protons, okay? And then we have the delta. This is the so-called GCK mechanism, okay? And then we have the fluxes, these possible decays, right? Neutrinos from this possible, from the decays of these mesons, okay? And then we have neutron decay. In neutron decay, it's just neutron which decay into a proton, an electron, and an electron antineutrino, okay? So, but these are the three processes. So understanding which of the three processes have produced our neutrinos will be a clue to understand the origin of the ultra-high energy cosmic rays. Here you can see the gamma rays, the neutrinos as detected by IceCube, and also the ultra-high energy cosmic rays, okay, in energy, with the energy. This is the spectrum times E squared. So we expect similar energy in gamma rays, neutrinos, and cosmic rays from cosmic sources. So, I mean, all of them it's not that one can understand one without understanding the other, right? That's why we call this multi-messenger astronomy, okay? So, this is a plot that you have seen, right, already in Francesca's talk, okay, lecture. So, I mean, we have here the knee, the ankle, and here we have this huge, this very, very ultra-high energy cosmic rays. We expect less than 1 particle per kilometer per century, imagine. So that's why we need huge detectors, as Pierre Oyer, right, that they really, really cover kilometers square of land, because otherwise we are not going to see anything, okay? So, I mean, here you can see that these are the different measurements of ultra-high energy cosmic rays here of high energy cosmic rays. You have seen that there is a transition between galactic and extragalactic, right? So the detection of PV neutrinos allows to study the sources of these ultra-high energy cosmic rays, right? Probing this transition, okay? So ultra-high energy neutrinos in the EV range will be crucial to investigate the origin of the accelerators of the ultra-high energy cosmic rays, okay? And ultra-high energy gamma rays cannot be observed except for things that are very close, right? And then ultra-high energy neutrinos instead can be observed because neutrinos interact very weakly, okay? That's why neutrinos are very important, because they don't interact, basically, okay? Gamma ray bursts, blazars, and also others are among the candidate accelerators of ultra-high energy neutrinos, okay? So neutrinos can also be produced in very dense environments where photons get absorbed and neutrinos can go out. And this is precisely what has been detected. You have been so lucky. November 4th, I mean, less than 1 month ago, right, there was a claim, well, there was a claim, no, there was a discovery from the IceCube collaboration of a source, right, of high energy neutrinos, right? They have detected this source, right, from the active galaxy NGC, not Galactic Cup 1068, okay, or whatever. So I mean, this was announced in November 4th, okay. So I was so happy. I mean, I was looking there to the press release. I mean, my husband was driving the car to a dinner, and he was like, "You are crazy." And I was like, well, we were going to a dinner of a conference. I mean, so anyways, all related to physics. But I mean, I was so happy. So some time ago, there were coincident observations from a high energy neutrino event, and also X-rays and gamma rays from a blazar, right? So neutrino production should be together with gamma ray production, okay? But maybe these gamma rays, right, due to the interaction with the CMB and the extragalactic background light, appear in X-rays or gamma rays, okay? So the gamma ray flux should be comparable to the neutrino flux. Is there missing electromagnetic energy? Maybe yes, because if the source is very dense, it will absorb all the photons, and we won't see the source in photons, but we will see the source in neutrinos. So I mean, the 10-year point source IceCube searches point to this object as the most significant steady source of neutrinos. And there is a model based on active galactic nuclei, right, that predicts that it should be the dominant source of neutrinos in the North Galactic Cup, okay, so in the northern sky. So gamma ray limits from Hess and MAGIC have demonstrated that it should be a hidden source, okay? Hidden neutrino source in the sense that there are no gamma rays coming from there, okay? So here I show you this cosmic obscure accelerator in the Messier 77 galaxy, and this galaxy is known since 1700 something, okay? It was discovered long ago. So it's a non-jet AGN with an obscure black hole, okay? And we can see Elisa Resconi giving this big announcement in this public, in this press release they did. And I don't know if I can, because if I do like this, maybe I make a disaster, but okay, I mean. So there is a movie also, if you want to see it, it's very, very nice. And I mean, I'm not going to touch anything because otherwise we can have, afterwards we need to fix again back all this stuff, so better not to. So I mean, this cosmic obscure accelerator has ultra-hot gas here, a supermassive black hole in the center, and there is an accretion disk, okay? This is the galaxy, this Messier 77, and you can see here, right, nearby active galaxy emits neutrinos, and here the most important thing, right? So this source is quite different from the other blazar, which was found to be a neutrino source in 2018, leading investigators to suggest that there might be more than one population with contributing to the neutrino background, okay? So here we can see, right, that we can start already to study ultra-high energy neutrinos. So the fate of high and ultra-high energy neutrinos, fate, flavor composition, Arral by direction, time distribution, and energy distribution, okay? Let's start. These are the 4 most important properties of high energy neutrinos, okay? So arrival direction is isotropic, is not. So I mean, as I just shown you, you can see that IceCube identified 110 northern hemisphere candidate sources, okay? Here we see this TX and these other sources, right, the most important ones. So here you can see a zoom, right, in the declination and the rise ascension of this source. And there are 79 plus minus 20 roughly detected neutrino events. This means a global significance of 4.2 sigma. So we are sure we have discovered a source of high energy neutrinos. And this, to me, is a Nobel Prize. Okay, to me. My husband says no, but I say yes, okay? I mean, just to fight. So, and my kids say, shh. So, anyways, I think this deserves really a Nobel Prize. So, here you can see a high-resolution scan around the most significant location of the source, right? This source, this NGC 1068. And then you can see the distribution of events, right? You can see here the signal, the background, the total, and the data, right, that fits perfectly of the neutrino events as we move out from the source, right? So you can see that it's amazing. I mean, this result, okay? It's really a 4-point-something sigma, which for cosmologists is a discovery, and for particle physicists is, okay, almost, because, I mean, we have to reach the 5 sigma, okay? Another fate thing, time distribution. We need coincidence with other sources, okay? So here I show you versus the energy, the flux, okay, times E squared of the events detected by IceCube here, right? And, sorry, here. And then you can see here, right? Sorry, IceCube here, sorry, here. This is a gamma ray data, okay? Gamma ray data, and then you have also the gamma ray observation, sorry. And this, you can, sorry, that is, okay. The emission model, which is this one, okay. The emission model for this source, right? Oops, sorry. Let me go back, okay. So you can see here the best fit IceCube observations, the gamma ray observations here, the NGC neutrino emission model, and here you can see these are electromagnetic observations, okay? So the gamma ray observations are only upper limits, but you can see that the model agrees perfectly with the spectrum that has measured IceCube, okay? So we really know how to, and these are the electromagnetic observations here, okay? For the gamma ray, I don't know what is the model. These are observations, all. For the gamma ray, there is no model here, right? There are 2 possible theoretical models here, but both of them are for neutrinos. These are observations of gamma rays. But I mean, realize that the electromagnetic observations are at lower energies. So what happens with this source is that it's an obscure source. All the gamma rays that produces get absorbed in the source, okay? So here I show you, okay? These are the diffuse flux measured by IceCube, okay? Diffuse flux. Isotropic flux. by ice cube. Here are the events measured by this source, the source of November, this NGC 1068, and here the spectrum measured from the other source, okay? So this means that there are plenty of sources contributing to these data points, okay? Because, I mean, we have just measured two. They are completely different, by the way. One is a steady source, it remains there, while the blazar is a time variable source, okay? But this should be that we are just entering into a very interesting era, I mean, so, you know, I mean, if you devote yourself to this, you will have a job for sure. Because, I mean, you will have to discover all the sources up to get here, right? So, I mean, so there are way more than one source contributing to the measured flux, to the diffuse flux, okay? And you can see this here, okay? The comparison of point sources, here, point sources, 2 point sources with the total flux. So, I mean, there are many other sources contributing to the extragalactic astrophysical neutrino flux, okay? We can also study the energy distribution. Does it follow a power law with a spectral index? It seems like, okay? So the best fit for this source is 3.2 plus minus 2, okay? So we are able also to measure, right, the spectral index of this flux that we have detected, okay? Flavor composition, okay? So for flavor composition, I should come back to neutrino oscillations. I briefly mentioned neutrino oscillations yesterday, but I should come back for neutrino oscillations. So just a parenthesis, a KitKat, whatever. So I mean, let me see. If you take a wave and you add another one of very similar frequency, you should see some sort of interference, right? Bits, okay? And now I want to go here, but maybe open link, okay? But you cannot see my screen now. I don't know why you can I do something like, yeah, but then I cannot play with that, you know. So, I mean, the thing is that, let me see again. What is it? Open link, and now it disappeared. Here it is, no? Isn't it here?
Browser?
Yeah.
The browser?
No, this is not the browser.
The browser, which one would you use? Do you use Safari?
But I put it in Firefox, but okay, doesn't matter. I mean, so let me see if I can do it like this. So here, right? I can do like this, right?
I'm not sure if you can. Say open link.
If I do like this,
okay.
and I go to Firefox, to whatever. Well, better to Safari maybe. Doesn't matter. But there is no sound anyway, so, but okay, I mean, I was just... No problem. But they cannot see, that's the problem. But then I cannot play with this. And displays, just super, if not, we forget about this. And that's it.
Maybe she can play with the screen output just to unir las dos pantallas en una. No puede hacerlo porque tienes igual para hacer eso.
Yo siempre pidiendo, pido más que, en fin.
¿Qué pantallas?
¿Dónde aquí?
En accessibility, no.
Será en display, ¿no? Displays.
Exacto.
Y era en no, pero no veo dónde están las dos pantallas para de compartir. ¿No?
Espera.
Así están preparados.
Y si vuelvo a...
Vete atrás, no que hasta flechita.
Aquí.
A ver, pantallas, ¿dónde están las pantallas?
Displays aquí. Es que no sé, no me pasa. ¿No?
Ahora, entonces, ¿aquí qué es?
Display settings.
Extender.
Main display, extended display probably, no? No, how can I come back? Yeah, but now I cannot come back to the other. Well, we'll see how to come back then after, no? Okay, so I mean, what I wanted to show you is...
Maybe you can play, I don't know, you can use this screen to play things.
Okay. Yeah, but they cannot see this, maybe?
Yeah, if you move it, they can see it.
Okay, you can see it. Okay, perfect. Yeah, but I cannot see it now. What do I do? Well, I mean, anyways, this was a play. Sorry, I made a mess. Stay here, please, because I don't know where to come back to the other. This is something that you can find on the web that is just like neutrino oscillations are like musical beats, okay? If you take a wave, another one of a very same frequency, and this is very nice, I can show you later on like this. So, I mean, what's that I used to each of these? So, I mean, you can see that it will appear as a bit, some beats, right? I mean, so if I can do like this, sound on, off, maybe? Yeah, now, yes. Yeah, volume, no? Yeah. So you can see that. Yeah, but I don't see this screen, that's why. So I mean, you can play with this and see how musical bits appear, okay? So now I come back to the other thing, if I am able to. Keynote, okay, very good. And now I don't know what to do, so very good. Let me go. So system preferences. This is challenging, eh? Let me see. Now it gets like system preferences.
It's here and there. It's there, right? So
Yeah, but
you want to bring it here?
okay.
So when you should first go back to
Main display. No, probably main.
main is here. No?
Okay. Done. Okay, very good. So now, of course, I switch off this, right? And then, very good.
Something, but not the public.
Okay, no problem. Okay, so you can go to that page, that web page, and play with this. It's just to make you understand that neutrino oscillations is just a pure quantum phenomena, and it's just something related to interference. Okay, so are similar to musical bits. Okay, if you take some wave and you add another one of a similar frequency, you will have this interference. So I mean, neutrino oscillations are the same, right? When one flavor fades, a new flavor shows up. Okay, and this can only happen if the neutrino is made of different waves, right, of two waves with a small physical difference, and that is mass, okay? So neutrinos are massive, okay? And here I show you that neutrinos mix, okay, as other particles, as in the quark sector, right? So if neutrinos oscillate, it's because they have mass, okay? So what happens is that we produce neutrinos in charge current processes. I just told you, for instance, in the case of pions and muons, right? But they don't propagate as mass as flavor eigenstates. They propagate as mass eigenstates, okay? And they are connected via this matrix, that is the Pontecorvo Máquina Kagawa Sakata matrix. Oh my God, I was able to say the whole thing. So, and then they are connected, right? So there are mixing between weak eigenstates and the mass eigenstates, okay? Here is the best fit for these parameters, right? Are just mixing angles, okay? And then what happens is that you can produce an electron neutrino, right? Undetected as electron neutrino, right? In a weak interaction, or you can produce an electron neutrino undetected as a muon neutrino, because neutrinos can oscillate, okay? So each mass eigenstate evolves just as a plane wave and acquires a different phase, okay, given by the energy times the time it flies, or I mean basically the length it travels, okay? And neutrinos are produced as flavor eigenstates, which are a combination of mass eigenstates. So you will have a non-zero probability of detecting another flavor of neutrino, right? So the oscillation probabilities are given by this expression, right? Because at the end, neutrino masses are very small, so we can do some approximations, and the oscillation probabilities are given by this expression here, okay? But in a two-family, considering two-family, just to simplify this, what happens is that we have, right, if, for instance, the mixing matrix will be just 2 times 2 mixing matrix with just one mixing angle. This will be the equivalent of the Cabibbo angle, okay? And then we will have either appearance or disappearance, right? If a new flavor appears, this will be appearance. If we are just looking how many of them have oscillated into another flavor, we are calling this disappearance. And the oscillation probabilities are just proportional to an amplitude, the sine square of the angle, of the mixing angle, times sine square of a phase. The phase depends on the mass square splitting. Remember that I told you that there are two, right? That there is the solar mass splitting, right, in the normal hierarchy, and the atmospheric mass splitting, or in the inverted like this, right? So these are the mass splittings, right? Delta m squares, right? The delta m square 1, 2, and the delta m square 1, 2. There are two of those, okay? So, and of course, neutrino oscillations depend on the baseline that the neutrinos have traveled, right? The distance, the energy, and on these mass square differences, okay? So The maximal effect, obviously, will be when the length is of the order of E over delta m squared. But for astrophysical neutrinos, you should keep in mind something. I mean, they travel over very, very, very long distances. I mean, the path length is so large, it's much larger than any possible oscillation length, relevant oscillation length. So we average over very rapid oscillations, and what we obtain is just this simple formula. So for high energy astrophysical neutrinos, right, also supernova neutrinos, that they have traveled for a long time, what we expect for the oscillation probabilities is just a weight of the elements of the mixing matrix, okay? So here we finish our parenthesis, and what is important here is that we will have neutrinos with a given flavor ratio at the source, okay? And then after traveling a distance, we have to map these, right, neutrinos, right, these initial flavors with this mixing matrix, okay, roughly. And then we will have different flavor ratios at the Earth, okay? But we know how to do it, okay? We know because we have measured this in neutrino oscillation experiments at Earth. So we know this matrix. So it's quite straightforward to map from what the source emits to what we are supposed to measure at Earth, okay? So here is just the mixing matrix, which is so-called is called the 3 by maximal mixing, but it's just this is UL nu squared. We have to multiply this by itself by its transpose to get the mixing matrix, okay? So important. This is let's play, okay? This is like a game, a board game, okay? So let's imagine we have neutrinos from pion decays, okay? Pion decays. For instance, those produced in collisions of charged pion decays. Those produced in collisions of protons with protons. They produce pions, okay? So we have nu e to nu mu to nu tau, 1 to 0, because pions decays into muons plus nu mu. And muons will decay into nu mu bar and nu e, okay? So we will get nu e to nu mu in a relation of 1 to 2, okay? Here, in this triangle, where are we? We will be here, okay? 0 tau, right? 66% nu mu and 0.33% nu e. You understand now the triangle? Have you seen these triangles before? Ice cube always is showing these triangles. Okay, so very good. Now imagine that we have neutron decay. Neutron decay, we have only nu e's, okay? We don't have nu mu's nor nu taus, okay? So where are we in this triangle? We are here because we are in the nu e 1, okay? And we don't have nu mu nor nu tau. And then let's imagine that we have muon damped thing, right? Sorry, in muon damped thing, sorry, nu e is here. This is the neutron decay. Muon is here, okay? It's because I have these two screens, and I'm like, this was already? Or, I mean, is the next one? Is the following one? And I don't want to touch it, because otherwise everything will be a disaster. So neutron decay, we are here, okay? Muon damped. What happens in muon damped sources is that sometimes synchrotron losses are very important. So muon don't have time to decay, okay? Don't decay. So this means that we have just the muons, the muon neutrinos coming from the decay of the pions. The muon does not decay. And then we are here, okay? Here. So I mean, when we take into account that the neutrinos come to Earth, right? We have to map this. So from pion decay, instead of having 1, 2, 0, we will have 1, 1, 1, because we have to apply this mixing matrix that I told you, okay? So if neutrinos come from pion decay, what we expect at Earth here is 1, 1, 1, okay? Even if the initial ratio was 1 to 0, due to neutrino oscillations, they will arrive as 1, 1, 1, okay? For neutron decay, right, that there were 1, 0, 0, there will be 5, 2, 2. And here, okay, 5, 2, 2. And from muon damped sources, from 0, 1, 0, we will expect 4, 7, 7. So we come from here to here, which means that this is what we expect to measure in ice cube, okay? Something like this, when we measure flavors, okay? when we try to extract the flavor in the ice cube, it should be something around there, okay? And of course, this assumes unitarity, everything should be some equal 1, okay? So, let's go. Pion sources, again. At the source, 1, 2, 0. This is the mechanism we have. You see, 1, 2, and 1 of those, right? Because for each muon, we have an electron or a neutrino or antineutrino, okay? But this is translated at Earth as 1, 1, 1, okay? From muon dump sources, we don't have this. This has no time to decay, okay? So we have just 0, 1, 0 that is translated into 4, 7, 7, okay? Just muon sources, okay? We don't have this, right? So muon sources only, we have 1, 1, 0, okay? If just muon decays in the source, okay? That will be translated into 14, 11, 11, okay? And neutron sources that we have 1, 0, 0 will be translated into 5, 2, 2. So that's how that's why we need to know what are the flavors. I mean, when ice cube people are in front of a computer looking at either it's a track or it's something like a shower, it's not because they are crazy. It's because they want to know which mechanism is operating to produce this. And this is very important also to understand ultra-high energy cosmic rays, okay? This transition from the galactic to the extragalactic thing. So what has ice cube measured? Ice cube has measured this, okay? These bounds here, these contours here. So this is theoretically what we expect from the different sources, right? These points that I just shown you, right? These points here, this star, this circle, this is what we expect, and this is what ice cube has measured. So from ice cube now, it's very difficult to see if it's PP, if it's P gamma, if it's pion, if it's neutron decay. But as we collect more and more and more data, these contours will be smaller and smaller and smaller, and eventually we should be able to identify which mechanism is producing these neutrinos, okay? Now, the glass-out resonance. Who knows what is the glass-out resonance? Very good. Who knows who is glass-out? Glass-out, who was, okay, you know glass-out, right? I mean, so anyway, so, yeah? So, I mean, Nobel Prize. I mean, for the standard model contributions and such, so after 60 years of that this resonance was theoretized, let's say, was proposed, IceCube has measured it, okay? So this is just an enhancement of the S-channel neutrino electron scattering, okay? So in the PV range, a W boson can be produced, right, from two processes, either electron-antineutrino scattering on atomic electrons or neutrino nucleus, okay? So this one, the electron-antineutrino scattering, produces the glass-out resonance. This is a resonance, you see, right? Is when something is produced in a resonant mode, okay? This is the production of the W boson in a resonant way. You can see here the process, okay? You see nu E bar plus E minus W, right, decaying into huge shower of particles, plenty of particles, okay? You can see the cross-section here and see that when the center of mass energy equals the W boson mass, we have resonant production of this, which means that this cross-section is maximized. Here we have the decay width and such. The resonant energy is just 6.32 PeV. So here you see the flux times the energy squared versus the energy. These are, again, ultra-high energy cosmic rays. These are the diffuse gammas measured by Fermi-Lat, okay? And here we have the events measured by IceCube, okay? Some of them are upper limits, some others are events, right? Either tracks or showers. Showers are induced by electrons, taus, and neutral current muons. Tracks are created by muons, okay? By muon neutrinos, sorry, okay? So electron neutrinos, tau neutrinos, and muon neutrinos in neutral currents leave showers, and muon neutrinos in charge current interactions produce tracks. Okay, we will see this later or tomorrow in detail. Okay, so here you can see this event, right, which is perfectly consistent with this, and this is perfectly consistent with the glass-out resonance. Okay, so Here I show you, again, the resonant energy, and the data is consistent with an hadronic shower with an energy of 6.05 plus minus 0.7 PeV, okay? So here I show you from this paper from the IAC collaboration. These are the gammas that the event has produced, this event has produced versus time, okay? All these gammas. And here is the escaping muon from this process with its Cherenkov cone, okay? You can see this, so this is the display of this Glasgow event, okay? So why is so important, the Glasgow resonance? Because it can tell us, of course, as well, what mechanism is producing these neutrinos, and also the cosmic rays. So I mean, if the mechanism is P gamma, we expect nu E bar to nu E 1 to 3.5. If it's PP, we expect 1 to 1. And if there are strong magnetic fields, we expect no electron antineutrino in the flux, okay? So the Glasgow resonance can be used also as a diagnostic for the production of these guys, okay? Very good. So, for instance, if we have pion sources, okay, PP in the PP chain, in the PP channel or in the PP process, what we expect is the same in neutrinos and antineutrinos, right? So nu E bar to nu E equal 1 to 1. And since the Glasgow resonance is only, it's a measurement of nu E bars, it tells you how many nu E bars are you going to have. So, okay, pion sources, PP, nu E bar to nu E, 1, 1, okay? Now, if we have P gamma, right, the things will be different, okay? Because nu E and nu E bar now are not in a ratio of 1 to 1, are in a ratio of 1 to 3.5. So we don't expect the same electron neutrinos than electron antineutrinos. And since the Glasgow resonance is just precisely a measurement of the electron antineutrinos, we can really infer which mechanism are we dealing with, okay? And muon damp sources, what you expect is a nu E to nu E, nu E bar to nu E of 1, sorry, here, okay? Same than here, so it would be difficult to, from this side, because they are degenerate in this case, right? And P, from this viewpoint. And then P gamma, what you expect in muon damp sources is 0 to 4, okay? In P gamma, okay? So this is just to convince you that by measuring the flavor of neutrinos and by measuring also the Glasgow resonance, perfect, we can infer which mechanism is operating at the source, and discard some sources, okay? So, now, this is devoted to experimentalists, okay? So, this is how do we detect them, okay? So, in the TeV-PeV range, the opacity is high, but some neutrinos can travel still thousands of kilometers inside the Earth before interacting, okay? So high energy neutrinos are detected, right, by instrumenting cubic kilometer water or ice with photon detectors, okay? These are the so-called optical Cherenkov light, the optical Cherenkov detectors, okay? Which detect particles, which detect both tracks and showers, okay? IceCube monitors the northern sky, while CAME3Net and the previous Antares are monitoring the southern sky, okay? So this is because we have the atmospheric neutrinos, and then they can look only, they have to look only to whatever they have. We have the Earth in the middle, okay? Because otherwise we will, and of course also the atmospheric muon background, okay? So since IceCube is in the South Pole, looks to the north, to the northern sky, because it needs the Earth as a veto for all this mess, all this background that we don't want. Since Antares is in the Mediterranean Sea, it looks to the southern sky, because it has all the Earth as a veto, okay? So, for ultra-high energy neutrinos, the interaction length is extremely short, and therefore, detecting them, we have either to look for showers in the atmosphere, or interacting in rock, ice, outside the detector volume, okay? So, very important thing is the tau regeneration effect. Francesca has briefly mentioned this, so this is very important. The tau regeneration effect is the fact that the charge current, the fact that at the charge current interaction of a let me go back here, okay? The charge carrying interaction of a tau neutrino will produce a tau lepton that decays, again, after 10 or 100 of kilometers into another tau. So you see, I mean, even if the tau neutrino interacts, it will produce a tau that interacts, that decays, and produces another tau neutrino, and then you see they reach your detector. So tau neutrinos are crucial because they are regenerated. It's not that they just interact and they produce a charge lepton and that's it, as muon neutrinos, for instance. No, the tau lepton that they produce has time enough to decay and then to produce another tau neutrino. Of course, we detect them with less energy than the ones they have, but okay, still, they are a very, very promising way of detecting high energy neutrinos, okay? So the time delay, delayed decay length of a tau neutrino is given by this expression, which at 10 to the 8 GeV is kilometers, right? So the neutrino can interact inside the Earth, and then the tau can emerge and decays in the atmosphere, initiating huge, right? A huge Earth shower, okay, that can be detected, of course. And the neutrino might interact deep underground, and the tau decays before reaching the surface, but a new tau is produced and emerges and interacts, right? And interacts again. And then this is called the tau regeneration, which increases the chances of detecting tau neutrinos, okay? Here I show you some geometry of the thing. A tau neutrino comes here, and then, you know, I mean, this is the incident flux and such. Here you can see that if this is the incident flux, you will have here, depending on the angle that, this is the angle, these different lines, these different colors depict the angle that the neutrino, in which the neutrino has right? Imagine this is the tau, this is the angle, right? Here, right? So I mean, this angle, this. So I mean, if the neutrinos really come from very low, they will be absorbed at some point by the Earth at these energies, okay? But if they are like Earth skimming, like they just touch a bit, you see that the flux is much less attenuated, right? You see here, for 1 degree, the flux is almost, well, it's not the same than the incident flux, but still, right? But as you increase this angle, of course, even if they regenerate the tau neutrinos, some of them will get absorbed in the Earth interior, okay? So, I mean, I show you here the IceCube Neutrino Observatory. This is an animation. Well, I mean, you can see, right, that the IceCube neutrino, let me do like this, and see, now, yes. You see, right, a neutrino coming here, and it produces these interactions here. There are optical modules here, okay, these are the optical modules. We have photomultipliers here. There are strings in the ice, deep in the ice. This is the size of the Eiffel Tower as a comparison. So what it does, the IceCube Neutrino Observatory, is a Cherenkov ice detector. So it detects Cherenkov radiation from neutrino-induced showers and tracks from all flavor of neutrinos. I told you there are 2 types of topologies, or even topologies, tracks and showers. And the astrophysical purity, of course, grows with the neutrino energy, because the backgrounds fall more steeply within you than the signal, okay? So we are also sensitive to tau neutrinos that, via this regeneration effect, have cascade from very high energies to lower energies. As they produce a tau, then the tau decays, then so on and so forth, okay? So, I mean, these pictures are really amazing. Look, I mean, this is in the Mediterranean Sea. This is one of these optical modules. These guys putting them down the sea, right, in these huge lines, right, that we have with these different optical modules. This will be the future IceCube Gen 2 array. It's going to be extended in IceCube, okay? And here is the P1, the Pacific Ocean neutrino experiment here, that will be down 2,000 meters in the Pacific Ocean, okay? So we have also radio detection, not only optical detection, okay? Radio detection in ice, okay? So this was a very, very, very smart guy, you know, as Grasso. And as many of you, of course, which was Ascarian. And he noticed that there will be a coherent strong radio Cherenkov emission when a negative charge excess propagates, right, within a dielectric media, okay? So in dense media like ice, there will appear compact electromagnetic showers, right, generated after the ultra-high energy neutrino interactions, okay? So they will produce a coherent radio emission, okay, at the given Cherenkov angle, of course. So I mean, in the fully coherent regime, this signal grows quadratically with shower energy, and it dominates above PV, okay? So experiments based on this Ascarian effect, this coherent radio emission, has been built as Anita, Ariana, Ara, IceCube Gen 2. Well, Gen 2 will be built, but so far we have Anita, for instance, right? And we need to look for either rock or salt that are possible radio clear media where neutrinos can have this Ascarian effect, can shower. So we have, for instance, radio detection in the ice by Ariana. IceCube Gen 2 also will have a part of the optical Cherenkov detector, that they will have these lines, right, these optical modules in ice. They will also develop a radio array, ARA, RNOG, right? All of those are based on this radio detection of ultra-high energy neutrinos. So Anita, I don't know if you have heard about Anita, and moreover there is some controversial thing with some events that have detected. Have you heard about these Anita controversial events? Yes? Okay. So I'll go through this now. So I mean, Anita is a balloon, right, that has, imagine, an effective telescope aperture of roughly 250 kilometer cube stereo radian at these energies, right? So this is the field of regard. This is the Antarctica, right? So I mean, what it looks like, what it looks for is radio emission, this Ascarian coherent radio emission from neutrino interactions in the ice, okay? So it's a balloon, and it has recently been, not very recently, but it has been a lot of attention to Anita, because there have been two anomalies, okay? They come in two types, either steeply upcoming Earth showers or near horizon Earth showers. So there are two anomalies. It has detected 4 events that they come basically like this, and 2 events like this, okay? So the steeply upcoming, those that are coming very, like at an angle that, well, it's not 90 degrees, but it's like 30, okay? Maybe due to a possible Earth skimming new tau. But this is in a strong tension with predictions of the standard model cross-section. Why? Because at these angles, these neutrinos, if the standard model cross-section is correct, that we believe it is, I hope, they will get absorbed, right? Okay? They cannot, because I mean, of course, they can produce this tau regeneration, but if they really are like this, if you are like this, you have a strong cross-section and they will be absorbed, these neutrinos, okay? Won't make it to the detector, okay? So the other near horizon are more consistent with Earth skimming neutrino events. Earth skimming are neutrinos that are just crossing the Earth at a very small angle, okay? Than these other events in terms of the distributions of the arrival direction and spectral characteristics. However, even though these have strong tension with I'm done. With Pierre limits, okay, and also with Anita's limits. I mean, with even Anita's measurement, they are in tension. So I mean, so you can see here, this was one of the first papers, right? And in which they claim this, but you can see that the angles, are really, I mean, 27, 30 degrees. I mean, they will get absorbed. And then the other paper, right, that in which they explicitly say that they violate limits from Pierre Auger, but in this case the angles are much more like, as I told you, Earth skimming neutrinos, okay? So this is my last slide. So there is a strong tension, you see. These are the Anita observations, okay? And this is the limit from Pierre Auger. So I mean, there is a strong tension with Pierre Auger observations across all energies, and also in tension with own Anitas in this side here. Look at the limits from Anitas and look at Anita's limit before, I mean, that they have obtained, and now what they claim. So, I mean, it's not clear. I mean, it certainly cannot be induced to that. Okay, so tomorrow I will just continue with this brief thing, and since I talk so fast, I'll have some time, and I will have some time to talk about the role of neutrinos and the Hubble constant tension. I think I have time. So, okay, thank you. You cannot see anything. Okay. No.
Hi.
Yes, hi, Mateo. Yeah.
I have just a curiosity. I mean, what else could it be? This anomaly. They are seeing light from the ice, so it's not just cannot just happen like that. Or is the?
I mean, there are some beyond the standard model possible things, like, I mean, some weird particle that the neutrino, neutrino with some any other extra interaction, right, that decays into a weird particle that after decays and produces a shower, you know? Right. So there are some there are some things like this. I mean, it's really strange because realize that these limits are quite strong, right, and quite robust, right, especially those from Oye. So, I mean, it's unclear yet. Especially, I mean, the ones that are Earth skimming, they could perfectly be, even though they violate these limits, but okay, I mean, maybe neutrinos have exotic interactions, I don't know, you know, I mean, but the other ones are really weird, because, I mean, it's true also that we have not measured, I mean, with man-made experiments, I mean, the cross-sections at these energies. So, I mean, you can expect new physics there, of course. I mean, if there are, I don't know, if there are in models of extra dimensions, I mean, at these energies, neutrino cross-sections can be notably higher, right, larger, and, or smaller or reduced, you know, I mean, depending on the mechanism beyond this, right, beyond your model. But I mean, it's not yet, it's not clear. There were like, I don't know how many papers. I mean, I think that one of my collaborators have a paper on this. I didn't write a paper on this. I should have, but okay.
Okay, more questions?
Hi.
Hi, thank you for the interesting talk. So
Thank
I
you.
was wondering that in Ice Cube and in Anita also, so there's a few papers that they are trying to find new physics in the new tau sector. So can you comment anything that why they are particularly targeting this channel?
I mean, because when you, for instance, for non-standard neutrino interactions, the less constrained sector is new tau, sorry, okay? Because, I mean, basically, I mean, you need higher energies to test. There have been much less experiments to produce a new tau is way more difficult. I mean, you see, I mean, how many neutrino beams we have of electron and mu neutrino beams. Basically, all experiments that have measured non-unitarity departures or non-standard interactions, right, are in the E electron and muon sectors. The tau sector is much less difficult is much more difficult to constrain, because to produce tau neutrinos is not as simple as that. We have opera, for instance, you know what I mean, but okay. So that's why you have more room there in the neutrino tau sector, okay? So, and remember that the only explanation for that can be neutrino taus, which are the ones that are regenerated. The other ones disappear, okay? And even tau neutrinos will disappear if they cross the Earth at a very shallow angle, let's say, right? I mean, are not just Earth skimming. The other ones cannot make it to the detector, because at these energies, the neutrino cross-section is high and they get absorbed. That's how, indeed, that's how these experiments put limits on the ultra-high energy neutrino cross-sections by this absorption effect. So it's only tau neutrinos, the ones that can make it. On the other hand, tau neutrinos is the sector less constrained by other experiments, by other measurements.
I have two questions. One, why Pierre Roger and no Ice Cube? I mean, Pierre Roger is also...
they put limits on they are also sensitive to tau showers, you know, I mean, to showers induced by tau neutrinos.
And Ice Cube doesn't have any...
No, because, well, Ice Cube at these energies, I would say, does not, might have limits, but that has not measured anything. Okay. Ice Cube Gen 2 should be able to test this hypothesis. But what happens is that precisely because of these Earth skimming tau neutrinos, they produce Earth showers that can be detected by OJ, by imaging detectors. I mean, indeed, there will be experiments in the future that are expected also to measure tau neutrinos via exploiting the very same mechanism that Oye.
Okay.
That's why everything comes together. So.
And the second question is the cross-section, no? Because in order to know whether they are absorbed or not in the standard model, you need to do, I guess, a complicated calculation of neutrino deep inelastic scattering with crap. In general, I mean, any kind of nuclei that could be inside the Earth, no? So how well is this calculated? Is known?
I mean,
is people are calculating the things?
I mean, at these energies, there could be even factors of 3, 4, 5, depending, for instance, on the Barton model, on the description, right? I mean, because realize that these cross sections are in a region of, for instance, the Bjorken variable. Tomorrow I will say something about this X that is very small, and this has not been measured by. So I mean, it depends. No, at these energies we don't have any data, and calculations can range factor 3, 4, 5. You know, I mean, depending on the underlying model describing the nuclear medium. Yeah, exactly. The particle distribution functions. Yeah.
Mine is very naive question. So they embed all these detectors deep into the ice, and then you said that I infer the answer to my question from your previous answers. The cross section of neutrinos depends on their energy, right?
Correct.
You say that very high ultra energetic neutrinos get absorbed if they go from below somehow.
Yeah.
They have to cross the whole Earth. But not the other ones, the low energy neutrinos. So the reason of embedding the detectors deep is just you follow the trajectory, you discard the atmospheric neutrinos, and then you're sensitive to the low energetic neutrinos that come from below.
Yeah, exactly.
Right?
High energy, when you look to high energy, yes. When you look into ultra high energy, the cross section is already so strong that they get attenuated.
They get attenuated, and then in that case you're only sensitive to
above
close to the
PV,
horizon.
let's say,
Okay.
And then you have to look for these tau events,
Okay.
this Earth skimming.
Pardon my ignorance. I remember when I was many years ago in the US, they had John Bacall had just detected the neutrino oscillation, but you mentioned atmospheric neutrinos.
He was solar. Yeah.
So was it atmospheric neutrinos or solar neutrinos?
Well, I mean, the solar neutrino deficit was much earlier the atmospheric one. Okay. So neutrino oscillations were already up high, let's say. I mean, they were already there. But I mean, let's say that the largest thing came in 1998 with atmospheric thing. I mean, when you observe the same in atmospherics, it's something like something is going on.
That Bacall's result was from 2000.
Earlier
than those. Okay.
Well, I mean, the solar neutrino deficit is older than the atmospheric one. Yeah.
Okay, but then the oscillations, the measurement of the oscillations, the famous physical review letters from the early 2000s with Carlos Peña Garay.
Yeah, these were afterwards, but this was also due to SNO and other experiments, right?
Okay.
But I mean, the solar neutrino deficit comes very early. Very early. But I mean, neutrino oscillations, let's say that were 2000 around, and I mean, now they have been robustly established and such. So. Yeah.
Thanks for your talk.
No, thank you.
More questions or are we just dead hungry?
Tomorrow. Tomorrow I'll tell them also about this Hubble tension a bit, and the neutrinos and such. I mean, because they had already lectures about the Hubble tension.
Yeah, they have heard quite a bit.
Well, yeah, you can solve. Neutrinos can solve everything. I mean, so.
Everything. Put a neutrino in your life.
Yeah.
Okay.
Put a neutrino in your life.
Thank you, Olga.
Thank you.